We present ZeroScatter, domain transfer for long-distance imaging and vision through scattering media. Adverse weather, such as fog and snow, negatively impacts both human and computer vision. Handling these unfavorable conditions is critical in order to enable safe decision-making and avoid fatal car accidents. We present ZeroScatter, a domain transfer method that removes scattering media in order to improve long-distance vision under adverse weather. ZeroScatter is built for RGB cameras, which has been commonly used across application domains from smartphone cameras to automotive imaging systems. ZeroScatter converts RGB captures taken in adverse weather into clear day scenes and operates at real-time frame rates of 20 frames per second. Removing adverse weather effects is a challenging task for several reasons. First, dangerous adverse weather conditions are rarely encountered in day-to-day driving. Most regions, on average, experience dense fog 12 times per year, heavy snow 13 times, and extreme precipitation 5 times. Consequently, these conditions are heavily underrepresented in existing datasets. Furthermore, it is virtually impossible to acquire paired perturbed and clear real-world data of the exact same scene. As a result, there are few real-world datasets for supervised training. To overcome these challenges, we employ indirect supervision using a novel combination of both synthetic and real-world data. This combination allows ZeroScatter to better generalize on real-world data over methods that are trained only on synthetic data. Specifically, we employ model-based, multi-modal, multi-view, and temporal learning queues as indirect supervision in order to train ZeroScatter on real-world data without paired ground truths. We'll explain each of these training queues in turn, starting with model-based supervision. Our model-based supervision consists of 2 learning cycles. The first cycle is clear to scatter to clear, and starts with an RGB image taken under clear daytime conditions. We apply an adverse weather simulator to overlay synthetic scattering effects onto the image. ZeroScatter then converts the synthetically perturbed image into a clear daytime scene. The other cycle follows a similar structure and goes from scatter to clear to scatter. It starts with a real-world adverse weather scene. ZeroScatter is applied to remove the scattering media, and the scatter-free output is then synthetically perturbed using the same adverse weather simulator. Utilizing a fixed adverse weather simulator instead of a learnable mapping ensures that ZeroScatter is able to remove various intensity and depth-dependent effects. We now discuss our multi-modal indirect supervision. Each RGB capture of our dataset is paired with a corresponding gated capture acquired by a specialized gated imager. Gated imagers are new types of sensor that use active flush illumination to acquire high-contrast images by gating out scattering media. These sensors only record illumination with a specific travel time, which allows the camera to effectively see through adverse weather artifacts, and to only emphasize objects at a certain distance. In contrast, RGB cameras would record all content in the scene with equal weight. To employ the gated capture for indirect supervision, we first pre-train an RGB to gated network, which infers the corresponding gated image for each output RGB image to account for the domain shift between gated and RGB images. Then we compare the result to the corresponding real captured gated image. This indirectly encourages our model to output scatter-free images. We emphasize that our use of gated images is only for training supervision, and that ZeroScatter only requires RGB inputs at test time. We now discuss our multi-view and temporal supervision. We employ temporal and still row training queues for encouraging consistency. The motivation here being that snowflakes, as well as other artifacts such as sensor noise, change rapidly between temporal frames and between different camera viewpoints. By enforcing temporal and still row consistency, we teach the model to remove these artifacts and to better facilitate downstream tasks, such as object tracking that rely on temporally consistent video. Our consistency supervision works as follows. First, We warp the multi-view and temporal captures with respect to the current left viewpoint. Consistency loss is then calculated by comparing the processed output of these warped images against the processed current left viewpoint. This ensures that ZeroScatter will produce consistent outputs for downstream tasks. Our proposed approach significantly reduces scattering media effects present in the scene and works under different adverse weather types. We now showcase the performance of ZeroScatter on unseen real-world adverse weather captures. Our first example is of a heavy snow scene, where ZeroScatter reveals objects at long distance, such as a house at the end of the road. ZeroScatter also performs well under dense fog. Here is an example where it removes the haze and reveals pedestrians crossing the street. Here is another example where ZeroScatter removes scattering media in heavy snow and reveals a far-off house and trees. This is a highway scene where it is snowing. ZeroScatter removes the scattering media and allows us to see further into the distance. This is another dense fog scene. ZeroScatter significantly reduces the haze and shows a better view of the intersection up ahead. We propose ZeroScatter, a novel approach for removing scattering media from RGB camera captures. We trained it on a combination of synthetic and real-world data through a unique combination of model-based, multi-modal, multi-view, and temporal training queues. Our method significantly reduces scattering media present in adverse weather scenes and reveals objects at long distance.